today is on the simple harmonic motion, that is experiment on the use of a spiral spring. So under it, the method calculation under this topic is what I will first of all explain. So after you have plotted in your graph, they may ask you to find elastic constant, because the topic itself, the experiment itself comprises of two different topics. One from Hooke's law. Then under Hooke's law we have F is equal to KE. And this K is called elastic constant or stiffness of material. They may now ask you to calculate this elastic constant. How will you do that? It's very simple. Just relate this topic to the theory part of simple harmonic motion using spiral spring. In that case, we have T is equal to 2 pi square root of M over K. Now, under the topic, under the table, we are going to have a column for T square. And you have column for mass already. If you look at the table, I have T square here. Then, see, under that graph, they will now ask you to plot the graph of T square against M. So you find the means of getting T square from here. You are going to have T square is equal to 4 pi square M over K. So if you have plotted this against this, the whole of this one is your slope. So whatever you get from the slope, let's say that my slope, I have 20. So I got 20 from my slope. I'll just equate it to this one. I'll now have 4 pi square over K is equal to 20. I'll just make this K the subject of formula. Multiply that K is equal to 4 pi square over 20. That's all. That's how to get the K. Where the K is elastic constant or stiffness of the material used. Now, on our table, we are going to have column for mass, which is in gram. Length, that is the whole length you are going to measure from the spring. Extension. Extension is original length that we are going to call N0. You take it away from the whole length of the spiral spring after applying certain amount of load on it. Then T is the number of, time taken for the number of oscillation given. It may be 20 or 10 when you are using spiral spring. So in that case, we are going to repeat the experiment twice. The first one, T1, T2, you add it together, divide it by 2. So this ordinary small t is half rate t, which is also in seconds. Then the capital T is when you divide this average t by the number of oscillations you counted. You divide it, you get this one. Then you square this column to get this one. Then each of these title, you must include the what? The unit. Then the value you are going to write. The value of this mass, since they are going to be given, they will give the value of masses to use. So in that case, it may be 20, 30, 40, or 50, 60, 70, and so on and so forth. The value given to you when you want to write it on the table, it must be in at least one decimal place. So if it is 20, you write 20.0. Then this length, since you are the one measuring it, leave it in at least 2. Then this extension also must be in at least 2 decimal places. Time, you are the one measuring it, must be in at least 2. This column 2, T1 and T2, 2 decimal places. Then ordinary T, because you have divided something here to get this, it must be in what? At least 3. This one 2, 3. But this one, where we are going to have T square, must be in at least 4 decimal places. Not only T square, sine, tan, cos, logarithm, and square root as well. All of them, they must be in at least 4 decimal places. Now, let's go to the real practical and see. Now, I've made the arrangement already. This is the metal rule. This is spiral spring. This is retortion stand. Now, you measure the length, the whole length of the spiral spring like this. When you have not put in anything, that is your N0. You can see it's what? 20. Now, you go to this place, right? N0 is equal to 20 centimeter. Now, if you now put the first mass, this first mass, let's say the first one is 50. Place your 50. Then take your reading. That is 22. Now, you record it. The whole length, this when mass is 50, 50.0, the whole length is 22.00. Then our extension will now be this 22 minus this one, which will give us what? 2.00. So the next thing is to perform the oscillation. Now, I have two different stopwatch here. You can use this one for it. For this one, you start it from this side. It's starting. Now, if it comes, you still stop it from this side too. Then you return it from this side. Just make sure you change it to the mode when it's blinking in both sides. And if you don't know how to use this one, make use of this type. This one is very simple to use. To start this one, raise this side up. You can see it's working now. You count the number of oscillation. After counting it, moment is up to the number of oscillation you want, you press this one down too to stop it. Then if you want to perform the next one, you press it here to return it back to its original position, to reset it. That's all. Now, that is that for the first one. If the next one is 70, just add 20 to it. Then it's now 23. So you record it. And don't forget, the oscillation, if you want to do the oscillation, press it slightly and release it. It's okay like that. You count the number of oscillations given. For each value of mass you place, when it is 7 and 20, 50, when it's 70, and you record corresponding value of L, E, T1, T2, ordinary T, capital T, that is the period, then T squared. So that's just the summary of experiment on the use of a spiral spring.